Thanks, everybody. I'm going to then talk about building and deploying low-cost sensors and data loggers that may be useful within the context of the NEA. We have a whole bunch of resources that you'll get this link at the end of the session associated with this part of the talk, but also the other talks at this short tiny.cc URL, which I'll also show you at the end. So what is Freestation? Freestation is a solution to the problem that ground-based monitoring infrastructure is declining globally, and we can't remotely sense all the variables we need to measure. So that's an issue for monitoring on the ground. However, technological barriers to designing and building your own hardware are falling all the time. In particular, things like low-cost microprocessors, 3D printing, and easily purchased electronics on websites like eBay. So Freestation is environmental monitoring with open source, do-it-yourself hardware. It's much cheaper than buying commercial products, of course, but then you have to build it yourself. We estimate the cost is around 3% the cost of proprietary instruments, which means it's certainly within the realm of students and within the realm of schools and universities. And our designs are very much built so that they can be built by geographers. You don't need to be an electronic engineer. We're all geographers. And many of them are web connected for easy access to the data, as you'll see later. And this is a key focus of our undergraduate teaching and research at KCL Geography. Low cost doesn't have to mean low accuracy, low precision, or poor quality. Low cost is often largely because we're using non-specialist, consumer, mass-produced parts, and we're putting them together ourselves. And the fact that they're consumer parts means that the prices are much lower than custom-built parts. So why would you build a sensor? Why not just go and collect data with a quadrat and other sort of, let's say, manual devices? Well, sensors in the field, in the garden, or even in your home, in your house, NEA dissertations can be done in the house, in the garden, in the allotment, in the vegetable patch, allow you to collect much, much more data than you can do by hand. You can collect data when you're not there, and you can do so frequently over time. You can collect a wide variety of measurements using sensors that you can't collect through manual methods. These data provide the environmental context for a range of dissertation topics, covering social science as well as many different aspects of physical geography. And collecting data using sensors in different places enables us to do geography, to understand the difference between one place and another, even if those places are only a few meters apart. So we can do field, garden, and home experiments, during rainfall events, for example, if we're interested in that, in addition to doing long-term measuring. So we can do experimentation as well as doing monitoring with this kind of equipment. Why would you build your own? Well, largely because of the cost, but also because you learn something, it's interesting, it's practical, it can be fun. You can use many more sensors, that's another reason to build your own. And you can work with others to have students building local monitoring capacity, empowering communities with the evidence on, for example, water contamination or anything else to influence their own situation. So what might be the relevance of that to the NEA? Well, Freestation instruments and low-cost sensing in general allows us to measure many different kinds of variables, which I'll say some more about later. But for each of those variables, one of the things we've done is put together more than 120 dissertation questions based on sensing one or more of these variables. So for example, if we're using our simplest sensor, which measures temperature, humidity, and air pressure, there's a whole bunch of questions that we can do here in the home, in the garden, or in the school grounds, that are dissertation questions that allow us to understand more about weather and climate and the relationship between different variables. And those questions are all online at the link you see there. And, you know, some of these are very simple questions. How does temperature and humidity vary with height from the ground? And how does this change with weather conditions, time of day, and ground cover? They're simple questions, but they actually allow us to understand things about the environment. You know, a black tarmac surface creates a different temperature profile above it that compared with a white one. Well, what are the implications of that? Well, there are implications for the urban heat island and so on. And we can do this in an experimental way, or we can do it in the form of monitoring over time and understanding relationships. So, you know, even with just the simplest of sensors, there are lots of questions that we can ask and answer. What do you need? Well, you don't need a big workshop. These are designed to be built with a very simple set of tools that you see there. You know, a soldering iron is needed, some tin snips. If you're going to have weather stations outside, they need to be protected with metal against sunlight. Something to bash metal with, a glue gun, a drill, a screwdriver, and so on. Not a lot. You need a bench to do it on. You need steady hands, safety gloves, protective glasses, and all of that. You need to be able to follow the instructions, of course, because you can easily go wrong if you don't follow the instructions. And you need to be able to, when you put this thing together and you realize that, oh, it doesn't work, you need to be able to take it back apart and say, well, what have I done wrong, right? And how can I get it to work? And if it doesn't work, it is because you've done something wrong, because we have built hundreds of these, and so the designs do work. There's no magic in electronics. If it doesn't work, there's a reason, and you know, the troubleshooting tips will help you or your student or whoever's helping your student to find out. And of course, you need time. You're not going to be able to build an instrument to do measurement, and your students aren't going to be able to if they want to do measurement the next day. You know, it takes time to do this, time and tea. So how do you build with Freestation? Well, as I said, we have well-tested, widely deployed open source designs. We have more than 300 stations in 16 countries, and that data is also available for any dissertation work. We'll talk about that later. They're buildable by geography students. All of the parts are bought on eBay. We use two platforms, either Arduino, which is a well-known platform like Raspberry Pi, or Particle, which is an internet connected, either Wi-Fi or 2G platform, and something called a printed circuit board. Now, a printed circuit board, if you can see my picture, looks like this. This was designed in order to make it easy to do this, because each of the components that you buy, you just solder it onto that printed circuit board. There's only one place that it can go, and there's only one direction that it can go around. And then if you put it, if you've soldered it in place and you plug the component in, it will work. So everything is plug and play. You upload the firmware, which is the software that runs the device, and there you are, off you go. So they're relatively quick to build after you've done the first one, and all the instructions are provided. What can you build? Well, you can build weather stations like that one there that measure things like rain, fog, wind-driven rain, air temperature, humidity, sunshine, photosynthetically active sunshine, wind speed and direction. You can monitor soil moisture in a plant pot or in the garden. You can look at water quality if you have a pond or something like that you're looking at. If you're working outside of your garden, there are projects that involve rivers. You can measure the height of river, which we call the stage, and the discharge. And then there's a whole bunch of different variables that you can also measure depending on what you're interested in. And in the 120 questions, each one of those variables has some questions associated. And then there are some other more sophisticated instruments, including a scanning LiDAR that you can build. I'd say that, you know, you need a bit of time for that, but that allows you to measure river profiles or create DEMs. And even that, the cost of that is £150. The others are much less. So here's a river level gauge, for example. Mostly this uses a parking sensor from a car to measure the distance from the sensor to the water, so that as the water rises, the parking sensor measures the height and therefore gives you the river level, and it does that every 10 minutes and records it every hour. Water quality, this one uses parts from a washing machine to measure turbidity, temperature and salinity of the water. Here's a weather station. This is doing soil moisture and rainfall. This is allowing us to do aerial photography with a long pole and a camera on the end of it, and a Freestation here that's allowing the control of that camera. And this is the scanning LiDAR that I was talking about, that allows you to do river profiles, as you see there. This device here is the most basic device, and so this is our classroom demo unit that you can build for £30. So the cost of the PCB, which is about 12, plus the particle photon, a Wi-Fi based IoT device, Internet of Things device, a battery pack, and then a temperature, humidity, air pressure sensor here. And so if your students are doing work in their home for a dissertation, or in their garden, in the home this could be used directly. In the garden you'd need to put it in a box to protect it from the elements, like a sandwich box or something like that. But overall you could collect data, good data, even with something as simple as that, and it can be connected to the home Wi-Fi network so that data is immediately available, or it will write to an SD card. And we use this for all sorts of things, all sorts of research questions. This is one of our current research questions. We are looking at the reintroduction of beavers in Essex, but they're being reintroduced in a number of counties of the UK. And here we have a pair that have been introduced into Essex, and we are monitoring the water levels behind their dams. This is one of their dams. They have 19, and trying to understand to what extent they are holding back water, and whether the amount of water they're holding back in their dams is sufficient to stop this, which is flooding of the village of Finchingfield downstream. And just using one of these and a few clicks of a button on a website, you can generate a live feed of how much water is being held back in this particular pond. And there are lots of other similar kinds of analyses that you can do. Here is another kind of project. Here we're looking at long-term monitoring. And of course, if you have school grounds where there is the possibility of putting a weather station, you could leave it there as a geography department year on year, and that would provide you with a database that multiple students could use and compare between years. You can also use this kind of monitoring equipment for experimentation. So it could be that in your house or in your garden, you set up an experiment to for example, look at the impact of opening the window on the spatial distribution of temperature in a room by looking at temperature in a variety of places around the room with different sensors, and then seeing how that changes in sort of 3 dimensions when the window is open or the door is open versus closed. So experimentation is also possible. And of course, if you're working with a field study center, or if you're working with other schools, or if you're working with local organizations who have an interest in the environment and geography, then you can work alongside them, as we are with this school, to support local capacity as part of these. A more long-term engagement that goes from student to student as they do the NEA from year to year. The key benefit of using low-cost sensing, as I mentioned, is that you can just sense a lot more in many more places, and spatial heterogeneity, spatial variability is the key to geography, and so many of the 120 projects that we list are about understanding differences over space, or differences over space under different conditions, or indeed differences over time. How do you start? Well, we have a website called freestation.org. The building section of that provides documentation like this, step by step with pictures, that tells you how to do each part. You start with building the sensor, then putting together the microcontroller on the printed circuit board, adding the SD card or the Wi-Fi, uploading the software to the device. You need a computer with a USB port for that, adding the batteries. In some cases, if they're deployed for a long time, you need to add a solar panel, putting it in some kind of housing to protect it from the environment. And as long as you follow the instructions carefully and fully, you will build these without problem. What if you want to build something we don't have a design for? Well, we have designs for lots of things, but we don't have a design for everything. And then I'm afraid Google is your friend. The chances are that someone out there has built what you might be interested in, or what your student might be interested in, and you will find some instructions on that. The open source community, whether it's in GIS or in low-cost sensing, is very open and very willing to share and very willing to answer questions. So if you were to build a simple sort of demo model for about £30, that's the one that I showed you, that looks a little bit like this. It has a printed circuit board. This is the Arduino version, and on one side it has an Arduino, that's the microprocessor. On the other side it has you can see a battery that is a real-time clock that keeps the time once it's set. It has a small screen, which we call an OLED, and it has an SD card for writing data to. The Arduino versions are cheaper to build, but they don't connect to the internet. They write everything to an SD card, which you then have to connect to your computer. This has a cable attached to it. We use standard cables for everything. This is an Ethernet cable for a computer. And then at the other end, there is a sensor. This is a sensor of temperature, humidity, and air pressure, called a BME 280. And as you see, it's just connected to the other end there. And so you can build that in an hour for about £30. And there you've got a data logger that will, every few minutes, wake up, take readings of temperature, humidity, air pressure, go back to sleep, and then write them every hour as averages. And you can then look at that data. And the components that are involved are just these for the Arduino version, right? The Arduino itself, the OLED, battery connection, SD card holder with SD card, a couple of jacks, which are how we connect the sensors in, and your real-time clock, right? You can't measure, no measurement is useful unless you know where it was taken and when it was taken, as well as the measurement value. And that's why you have to have a clock and you have to know where it was taken. So simply put, even if you're not using these in an NEA, you could have students in the computing department or geography students build them, and you could use these in class, right? So where the class, there's a practical here that just allows you to plug these together. And once you plug them together, attach a series of different devices, sensors, from a rain gauge through to a turbidity sensor, soil moisture sensor, wind speed and direction, and then look at the data that comes in. If you want to build a web-connected station set of sensors, then you need a slightly different approach. This approach requires the same kind of printed circuit board that we just looked at, but instead of an Arduino, we use the particle photon, which is Wi-Fi connected. We add a couple of switches and things. We have the jacks to connect instruments, and then the battery connection as well. And then when we do that, it looks a bit more like this. There's your printed circuit board. Everything is in the right place. There's only one place it can go. And this device you can connect, once you've uploaded the firmware, you can connect a variety of different sensors to, and then they write the data directly to the internet. So I will show you some brief examples of those. So here we have a variety of sensors. Now I plugged in this device here, which we call L64. When you first plug in a device that has the Freestation code on it, this is L64, the Freestation website where you go to will tell you, okay, that device has a number and it's L something, and this one is L64, and that number is your key to get the data for web connected devices. So I plugged this in a little while ago, and as you can see, I'm in my workshop, aka shed at the top of the garden, where I tend to do my Freestation work. And when I plug that in, L64, hopefully you can still see this on my screen, it started measuring. And what happened is that it started measuring. It was warm, the door was closed. So I opened the door and the temperature went down from 27, as you can see, to 25. I then closed the door again, and it's gone back up a little bit from 25 to 25.5, and then I opened the door again and the temperature's gone down. And this is the Freestation data interface, where you can download data, where you can visualize data and analyze data. If we wanted to plot that against humidity, we can do. Okay, not a lot happening in humidity. It's between 42 and 43, 44% dry. I can tell you that, and reasonably warm. But this is how we can collect data really easily. Once you've plugged that in, it connects to your Wi-Fi, you're running in terms of collecting data. So there's a whole bunch of these that just are measuring different things. I don't really have time to go through all of those now, but if we have time for questions at the end, I'll maybe show you a few more of those things. If you wanted to run a practical in school, then we have a guide to, building the classroom model and running a practical in which you buy a series of sensors, you build maybe 10 of these classroom devices, you plug different sensors into different devices, and then you have different students play with those sensors. Breathing on the temperature humidity probe will give a response in both temperature and humidity. Blowing the wind anemometer and so on will help to help understand how sensors work and how they convert a movement or something else into a value. And this guide here shows you how to build them and how to upload the firmware, how to retrieve the device, the data using an internet connection when your students are working with the devices. So I'll show you an example of how to access the system for data. Any Freestation writes data to this system, and you can access existing data from a variety of countries, or if you're building your own station, then you can access your own data as well. So here's one of our weather stations in Colombia, and we'll just use the interface a little bit. This is temperature, and you can see it's from 25th of December to the 31st of December, and you can see it's varying diurnally, of course, with the day-night cycle. We can look at that over the month or over the entire, and you see then we have 30 day-night cycles, or over the period from when it was put in, a number of months from August to December, and then we've got lots of day-night cycles. We can plot that variable against another variable. So for example, let's plot temperature and solar radiation together. When we do that, it's quite difficult to see, but clearly both have a day-night cycle. So let's examine that as a scatter. Is there a relationship between temperature and solar radiation? Well, there does seem to be. As solar radiation goes up, temperature goes up. It's not linear, it's non-linear. Why might that be? What's the scatter associated with it? There are all sorts of questions that we can ask. So if we go back to the line graph, well, let's look at how the two variables relate, maybe over a week rather than half a year. And indeed, you can see the solar radiation, that sensor costs only £6. Up and down, diurnal cycle, but with interruption by clouds. The cloudy periods cause reductions in solar radiation, and that, of course, drives the pattern of temperature that we're seeing. But there's something else as well driving temperature, and that's, of course, the air masses and all of that going on. And you see the weather station has a wide variety of different variables. If we wanted to plot rainfall, we could. There's a little bit of rainfall there, but not a great deal. Maybe over a month we have a bit more. And if we want to see how maybe rainfall and wind speed vary, well, let's do that. And we're going to auto range so we can see more of the variability. And it's probably too long a period to see clearly. So looking over the last period, we can see, yes, there's a diurnal cycle in wind speed as well, quite strong. There doesn't seem to be a huge association between wind speed and rainfall. So, you know, collecting data is now easy. Getting hold of the data is now easy. Analyzing the data is now easy, all thanks to open source technologies. So if you go to the Freestation website, one of the things you'll see is a map of where all stations are when they are connected. Those that are able to will geolocate themselves roughly to the nearest few kilometers. And so you can click any one of these and download data of the type that we just saw. And indeed, some of the 120 questions you could answer with existing data. You don't necessarily have to build. So how might you use this kind of thing in an NEA? Well, with sensors to view different elements of the world, NEAs or fieldwork investigations can take place in the home or garden and still be original and exciting. This is particularly useful during lockdown when actually there's probably nowhere else we can go than the home or garden. And so that helps us to do field work in a local context. First need to consider, if you're asking, trying to come up with a question, what variable you're interested in measuring. And that needs to depend on, how much work you're prepared to put into building the device. Things like air temperature and humidity are very easy to build. Water quality, a bit more challenging. So what variable do you want to measure? You then decide on a question. There are a number in the sheet that I mentioned. And those questions can either focus on how does that variable vary over space? For example, with distance from a road, or with distance from a wall, if we're measuring sound, distance from a road, if we're measuring temperature, maybe distance or wind, distance from a wall. How does it vary between different control settings? So how does this variable vary under a tree in the shade or in the shade of a building versus not? Because again, there are lots of interesting consequences of that variation. How does the variable vary over time? Between day and night is always an interesting one. But we might also want to look at the relationships between variables. So how does one variable change when it's raining versus when it's not, when it's day versus when it's night, when it's on this surface or that surface, or when it's windy, or not. Those kinds of questions are sort of peppered throughout this document. Or you might compare with a human driver. What happens to the room temperature when we switch the heating on? What happens to the noise levels when the diurnal cycle of road traffic occurs, and so on. Once you've decided on the question, you obviously then need to follow the instructions to build the Freestations, get parents involved, get your computing department involved. Many will be willing to help. You need to test the Freestations before they're deployed, deploy them. If you're not doing it in your home, garden, allotment, whatever, then you do need to get landowner permission before putting any monitoring device anywhere. If you don't, you can get into quite a bit of trouble. So be aware of that. If it's outside the school grounds, you need to get landowner permission. You then collect the data either by Wi-Fi or SD card. In the case of SD card, you then upload it to the website. It will analyze it for you, and you can either use the website or download a spreadsheet to answer the question that was set. So thank you. We have time now for questions. Quite a bit of time before we need to go back to the main session. We can either do questions or we can do a mix of questions, and I can show you some of this kit. So just let's use the Q&A for that, and John and I will come in as necessary. Okay, so one of the questions we have, whilst the techniques are very interesting, many of the titles wouldn't be ideal for an NEA because they need to have a wider relevance to other research. I think that, yes, true, but I think most questions that you can use monitoring for do have wider relevance. So if we were to go, you know, to that document, and I'm just going to have a quick look to remind myself of some of the questions. By opening that document, then, you know, many of these questions can be associated, clearly mostly they're physical geography, although many of them are you know, interact with human behavior. How does diurnal air temperature variation vary indoors versus outdoors? Well, there's, you know, the wider story there is around human health and around building quality and around different types of building and how they either, you know, protect humans from the elements in terms of how well they're built, or how effective they are from an energy consumption, therefore, you know, climate change mitigation related aspects. Let's just pick another one at random. To what extent is solar radiation decreased from an outdoor setting to a room setting? And how does this differ for north and south facing rooms and different window to wall size ratios? Again, you know, this is to do with an element of the environment that is important for human health. We need to get enough light and enough sun, both to reduce our energy consumption in heating and lighting and for our health. And understanding that gets us into that literature and into that understanding a little. So I think that's a few examples there. How does soil moisture react to rainfall events, and how does this differ for soil moisture probes at different depths? Well, this is clearly related with agriculture. You know, understanding how much water there is in the soil after a rainfall event is important in understanding how much flows over the land, because it's not in the soil, which contributes to flooding. But also, if water is in the soil, then it contributes to plant growth, important for agriculture, or it contributes to groundwater flow, important for dry season water resources. So I think there are possibilities there. So do we have any other questions, or would atmospheric CO2 or even CO2 in rivers? Chris, are you available to talk about CO2 sensing?
Yeah, I am indeed. Sorry, I was just replying to that as well. Sorry, I didn't quite realize what you were asking for, but now, yeah, it makes sense. There are various different types of CO2 sensors, some of which are extremely cheap. So if I share my screen really quickly. So there are some really cheap screens. What's going on? Sideways. Really cheap CO2 sensors, such as this one. If you Google, YouTube search CO2 detectors, Arduino, then there will be a load of different videos on how you can create these. A potential issue with these ones is there's not going to be a very precise calibration for it. So it won't necessarily say parts per million, parts per billion. To do that, instead, what you might want to do is follow our instructions on our GitHub page, which was answered to someone else when they were asking about gas sensors. On our GitHub page, under the air quality sensor, the instructions here are for, the specific instructions are for an NO2, which nitrogen dioxide, NO, nitrogen oxide, nitrous oxide, sorry, and ozone. So though these instructions are for those three sensors, all you really have to do is change out one of the sensors to a CO2 based version, or indeed you don't buy these sort of boards where they just have CO2 on them. So yeah, it's certainly possible. The easier way is using the YouTube videos, which I said before. That's extremely cheap, but this way is a bit more kind of accurate if you're looking for a set concentration. So X amount of parts per million, parts per billion CO2 in the atmosphere. Hope that's answered your question.
Great, thank you, Chris. So just looking through some of the other questions, there was the question on, well, mostly these have been answered in the chat, but the question on age, I think this is right, that sort of year 8 or 9 is probably the lowest. It really depends on the supervision and it depends on the time available. There's nothing particularly difficult here, but you know, for the Freestation designs, at least, you have to use a soldering iron, and you know, that is hot and dangerous. For the designs that Chris just showed at the GitHub page, that may not be necessary, the soldering iron. You may be able to wire things together. But mostly we have worked with undergraduates and with A-level students, but I don't see a problem at all with GCSE students doing this. I think A-level students it'll be easier for, and they'll take less time to do it. But as I say, no particular knowledge of electronics or anything like that is required. And there's not a lot that can go wrong. Okay, so we're happy to take other questions also on GIS. Where I can show you a bit more of the instrumentation and see what comes through. Okay, so let's do a bit of that. Hopefully you can see this. I'm showing you a rain gauge. This is a very cheap, again, rain gauge. Used to be sold by Maplin Electronics, built in China. It's a tipping bucket rain gauge. It uses a small bucket inside the device that you see here. And as water fills one half of that bucket, it then tips, and that makes a count on the microprocessor, and water starts to fill the other half of the bucket, and then it tips again. So not only does this tell you the total amount of rainfall, but it also is capable of telling you the rate of rainfall and how that changes throughout a storm. So there's a lot of potential there. Some other sensors. So this is a cheap 8-pound soil moisture sensor. And again, this can be bought online. And with this, again, connected with the same kind of cable to the Freestation PCB, you can measure soil moisture, which again responds to rainfall and evaporation and drainage into the groundwater. So there's all sorts of possibilities there for understanding agriculturally relevant or hydrologically relevant data. This is what I mentioned, the washing machine component. Most washing machines have one of these in. It's a turbidity sensor. The washing machine knows when to stop washing because the water is clean by measuring this sensor. It costs a few pounds, and we put it in water, connect it, and that tells us the turbidity, so how the concentration of particulates in the water, which is a useful measure of water quality alongside salinity and temperature, which tells us something useful biologically about the water. This is our distance sensor, which we use, which is a parking sensor, and we use it for river stage or river height and all sorts of other things. Pond height you could use it for, and it's a sonar. Bounces a signal off the surface and calculates how far away it is, and it can do that very easily. Can the soil moisture sensor be used for mobile sensing along a transect in an environment? Yes, it can, particularly using either the 2G or the Wi-Fi versions. You can have soil moisture sensors along a transect, and they can be writing either through the internet using 2G, 3G, or they can just hold that data locally on an SD card. You build another Freestation, which we call a Freelay or Freestation relay. You go to the sensors in the field. The Freestation relay connects locally directly to the Freestation. You don't need a Wi-Fi network, and downloads the data from the SD card, even if it's been running for months and months. There was another question that came through on, well, you know, if these sensors are in remote environments, don't we need to take care of them? Yes, you do. Of course, you can't leave things logging forever because rain gauges get clogged up with moss and you know, things get dirty. So you do need you know, to visit them at least once a month to make sure that everything's okay. Working as was suggested in the question with local partners is the way to do that. Whether it's another school and you're comparing, you know, you have a transect of schools, each of which has its own devices up the mountain or distance to the coast or whatever the transect is, or whether you're working with other organizations if you're talking about overseas. So those sorts of things, I think we've seen that. Wind speed and direction. Again, there are very cheap sensors on the market that are perfectly good. These cost about £14. There's your wind vane anemometer. Wind vane there that does wind direction, and anemometer also attached that does wind speed. Okay, and again, you know, the wind environment in urban settings or the wind environment in and around trees is very important in terms of wind-based hazards, but also in terms of other climatic meteorological variables and how they vary over time. So that's a whole bunch of different devices. We have a question on the GIS about ARC. Does someone want to take that? Chris, are you available for that?
Yeah, sure. And there are a couple of questions which I need to respond to.
Okay.
So ARC has just changed their licensing policy to reflect obviously the kind of circumstance we're in at the moment. At the moment, it is free, I believe, at least to use the ArcGIS Pro. I'm not sure how long that will last for. There was actually a really good webinar on it last week, which I'll send the link to in your question. But fundamentally, I think that at the moment it is free. It's not necessarily to say that it will remain free for the next year. So you'll have to watch that webinar to see on ARC. As both Mark and John kind of alluded to, generally in Kings, we've started moving away from using ARC just because there are a lot of issues. Also, ArcMap, in the long term, they're planning on stopping support for it. So it's actually, I believe it's on its last version already, and they're gradually phasing out the support for ArcMap, the kind of the Windows-based software, although they're planning on keeping the ArcGIS Pro, which is the online version. So I'll send the link to that webinar to your question, in response to your question. We also had another question on, is it possible to measure aquatic dissolved oxygen? Yes, it certainly is. Really quickly share my screen again. So to do this, you can use what we call the manufacturer of this particular part is Atlas Scientific. It's a bit pricey, but you can buy the kit. On their website, they also have really, really good instructions for how you wire it up, etc. If it's still kind of a bit complicated, because where does RX, where does TX go? Then also on our GitHub page again, we have the designs for a water quality logger, and so you can just follow that through and then kind of take out the unnecessary bits. So if you're not interested in measuring other parameters with it, then you don't need electrical conductivity, you don't need a pressure sensor. It's generally good to measure temperature whenever you're measuring anything else in water, because the readings will change quite a bit. So I'll send these links and kind of a written reply to your question, both the one on the ARC, the one on ARC, and the one on dissolved oxygen.
Great, thanks, Chris. So I'll answer the question on tips for siting around school grounds, so weatherproof, secure. Yes, I think this is always an issue, and certainly we've had instruments vandalized, but also eaten by animals all over the place. I think in terms of siting around school grounds, depending on what you're measuring, you have to site in order to be properly measuring that. So if you want a measurement, for example, of the local wind speed, it needs to be unaffected by trees. And so you need to be in a fairly open area. If you're measuring solar radiation, you don't want the instrument to be shaded, or sunshine, you don't want the instrument to be shaded at any point in the solar year. So so a nice open space is good for most things. And what we find is very useful is if the device has a label on it that clearly says what it is and what it's doing, and that it's low cost and that it's built by volunteers, you tend to get fewer problems. But also I think we do tend to put, fences around some instruments, just again to deter people sort of prodding them and so on. So it will really depend on the school ground. In terms of weatherproofing, the designs come with very good weatherproofing, both against water and against heat, which is an arch enemy of electronics is a lot of heat, and so if you follow the instructions on how to build the shields and the enclosures, you'll be fine there. So I think we should head back to the main session.